Wolf here, and I'm going to be going over target 2 of our unit 7 on electricity. And what target 2 is really looking at is what is the electrical force, right? So if I have a positively charged object and negatively charged object, we know that they're going to be attracted to one another. And if I have two similar charges, right, positive, positive, negative, negative, I know they're going to repel. And so if an object is going to change its motion, well, then that's because that there is a force is being exerted on it, which means that if you have a charge, that it's going to exert some type of electrical force. And so the question is, well, what is that electrical force, and why does it exist, and what are the factors that have an effect on it? So in order to determine that, we have an equation, and that equation tells us what variables affect my electrical force. So first of all, this is my electrical force. And we measure that just like any force in newtons. So then what are my other variables going to be in this case? Before we do that, take a look at this equation, and hopefully it seems a little familiar. Now, we haven't dealt with these exact variables yet, but in terms of having like two of the same thing right here, like a constant right here, and then having it divided by something squared, take a moment to look around the room. Where have we seen an equation like this before? Hopefully, as you guys look around, you guys see that it's very, very, very similar to the gravity equation, right? And instead of having two masses attracted to one another, we have two charges attracted, or in this case, could also be repelled from one another. So Q is going to represent the charge of an object. And we measure charge, so the unit of charge is going to be a coulomb, which we abbreviate as C. So what is a coulomb? I think it kind of just helps to have a conceptual idea of what it is. A coulomb it's almost like a bucket. It's almost like measuring buckets of either extra electrons on an object or how many buckets of electrons might be missing. So we could write that as coulomb is how many buckets, and I'm putting that in parentheses because they're really, really tiny buckets, of extra or missing electrons an object has. Okay. And then finally, our other variable is going to be r squared. And r squared is going to be, just like gravity, our measurement of distance. So what's the difference? Why do we represent one as d and one as r? There's really no distance at all, and honestly, it'd probably be better to represent r squared as just distance squared. So r squared is going to be distance, which we measure in meters. Okay, so then we have, in terms of what affects the electrical force, we have two charges. We also have the distance between those objects, and if we were to plug in numbers and divide them by the distance, we would get a number that would not be the electrical force. So in order to make this equation work out, we have to have a constant in order for all the numbers to work out. And so that constant is going to be k in this case, and that k is going to be 9 times 10 to the 9th. Right, and really quickly, look at that gravitational equation in the classroom, and think about what that number is and how does that number compare to our constant right here. And with that in mind, what does that tell you about the electrical force compared to the gravitational force? Which one might be stronger? Which one might be weaker? And the electrical force is going to be 9 times 10 to the 9th compared to the gravitational constant, which is, this is our electrical equation constant. It's 9 times 10 to the 9th, which is way, 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 way bigger than 6 times 10 to the negative 11th for gravity. So what that tells us is that gravity is a really, 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 really wimpy force, and the electrical force is much, much stronger than gravity. And that kind of makes sense, right? Like we had our balloon, and and sometimes it could get repelled, right, go like upwards by that electrical force, even though gravity's pushing it down. So you literally have the entire mass of the Earth pulling down on a balloon, and it could still go upwards due to an electrical force of just some electrons on an object, some extra or missing electrons on an object. Okay, Some extra things about the electric force equation is, unlike gravity, it's not just an attractive force, right? Your objects could attract or they could repel. And based on the number, whether we get a positive or negative for the force, for the electric force, that tells us if that's going to be an attractive force or a repelling force. So for instance, let's say I have a positive charge and a positive charge. I'm going to get a positive object, or sorry, a positive number for my electrical force. I have two of the similar charges. That's going to be a repelling force. What if happens if I have two negative objects? Same thing, right? A negative times a negative is going to give me a positive number. So anytime my electric force is positive, I know that that's going to be a repelling force. My objects are going to repel. Right. Contrastly, if we have a negative answer for my force, well, that would be because I have a positive charge here and a negative charge here. We know that a negative times a positive or positive times a negative is going to give me a negative answer right here. And I also know that opposites attract. So in this case, if I have a negative electrical force, I know that that's going to be a force that's going to be attracting those two charges. The other thing we could do is we could look at the relationship between the variables in this equation and have an idea of how they relate to one another. So for instance, if I look at this graphically, I'm looking at the relationship between one charge and the electrical force. And in other words, as the charge of an object increases, what does that do to its electrical force? And since they have a direct relationship right here, as the charge of an object increases, that electrical force is also going to increase. They're on opposite sides of the equal sign. All right, what about the distance between two charges and the electrical force? What's going to happen there as distance increases? Well, even though they're on opposite sides of the equal sign, remember that we always want to flatten the equation. And so if I were to get rid of r squared on this side, multiply it by both sides, it would now be over here, and r and the electric force would be on the same side of the equal sign, and when that's the case, they are inversely related. And so as my distance decreases, the electrical force gets less and less. We could also do that reversely and say, as my two charges get closer and closer together, my electric force is going to increase. All right, so now we have the equation down. We could also look at the electric force a little bit more conceptually instead of mathematically, and that's what we're going to do on the lower part over here. So what do I mean by that? Is there's going to be some times where you could have a positive test charge. And if you're wondering what a positive test charge is, just maybe pause the video really quick and read this right here. So when we have a positive test charge, we're going to be placing it in an area where we have some charged objects, right? So here we have an object that is a charge of 2 coulombs versus an object that has a charge of 1 coulomb. And we're curious how this object is going to move in this area under the influence of my objects right here, right? Like this one, it's being repelled by this object, but it's also being repelled by this object. So what's the net force on that object going to be? All right, to start off these problems, the best thing that you could do is take your objects and start color coding them. So I'm going to make my object to the left blue in this case. So I circle it as blue. I'm going to make my object to the right red in this case. So I'm circling it as red. This is going to really, really help me keep track of everything. Okay. So I'm going to first just focus on what's going to be going down between this charge and my positive test charge, and in terms of how it's going to affect this one. So I have two positive charges, which means that this is going to be a repelling force, right? Likes repel. And this has a charge of 2 coulombs, so I'm going to just draw a little arrow, and I'm going to make it blue going this way because it's repelling. That blue arrow tells me that this force is coming from this object. Now I'm going to focus on what the red object is doing. Now, again, I have two positives, so this is going to be a repelling force, so the force is going to be going to the left on my positive test charge. However, I have a charge of 1 coulomb compared to 2 coulombs. And since charge is going to be directly related, right, to the electric force, I know that this force is going to be half as much, since the charge on this object is half as much. So it is going to be repelling, but it's going to be repelling about half as much. So this ends up being the forces acting on my object. This looks really, really similar to what we had when we were drawing maybe like the applied force in an object versus the force of friction. The only difference is we don't have anything in contact with our positive test charge, right? This is a long-range force between our two charges right here. So let's say that I wanted to figure out what my net force on my object is, right? I know that this test charge is experiencing all these different forces from these different charges, but how's it actually going to move? We do the same thing that we did before, where even though it's experiencing a force going to the left, overall, the net force is going to be going to the right. So I could draw and grab a different pen. Let's do this in purple, I guess. My net force is going to be going to the right in this case.